So imagine this. You make a discovery that literally rewrites the rulebook for physics, but then you have to wait almost 40 years for the world to really get it. That's not science fiction, that's the incredible true story we're diving into today. I mean, can you imagine? That was the reaction, just pure shock. A Nobel Prize for a paper from 1985? It just goes to show you, sometimes the biggest ideas, the ones that really change everything, they need a little time to marinate.
Okay, so let's get right into it. The surprise itself. Who were these scientists and what on earth did they figure out all those years ago that's making headlines now?
All right, so the prize went to three physicists, John Clark, Michel Devoret, and John Martinez. And their big paper, the one that started it all, was published way, way back in 1985. What they proved was honestly mind-blowing. They showed that all those super weird quantum effects, the strange rules that govern the tiniest particles, don't just stay in the tiny world. Nope. They can actually show up in our big, everyday world too. Now, to really get why this was such a bombshell, you have to understand that for the longest time, physics kind of had a split personality. There were two completely different sets of rules for how the universe worked. It was like a tale of two different realities. So on one side, you've got the world we live in. Classical physics. It's predictable, it makes sense. You throw a ball at a wall, it bounces off. Duh. But then you zoom all the way down to the quantum world, the world of atoms, and things get weird. The rules just go out the window. A particle isn't just in one spot. It's kind of everywhere at once, like a little cloud of possibilities. And the craziest part? That particle can sometimes just pass straight through a solid wall. And this is exactly where our three physicists come in and just blow everyone's minds. Their paper showed that this super strange wall phasing trick wasn't just for tiny particles. No, they saw it happening on a scale big enough to actually see and measure. It was like they proved the wall separating the quantum world from our world, well, it wasn't a wall at all. It was more like a blurry, shimmering curtain.
Listen to this. We're not talking about one little particle getting lucky. We are talking about billions of electrons, all moving together, acting as one, and just phasing through a wall they should have bounced right off of. So how do you even wrap your head around that? It sounds impossible, right? Like something straight out of a comic book. People were calling it the ghost through the wall. And honestly, even the researchers felt like they were dealing with something that was more science fiction than reality.
Which leads to the million-dollar question. It just doesn't make sense to our brains, does it? It goes against everything we know. And believe me, physicists back in the 80s were asking the exact same thing.
Well, there's a name for it, of course. It's called macroscopic quantum tunneling. That's the fancy physics term for this ghost-through-the-wall thing. It's basically quantum weirdness, just supersized.
And the reaction from other scientists at the time? Pretty much this. Yeah. The results were so out there, so against the grain of everything they thought they knew, that most people just flat out didn't believe it. So you're probably wondering, how did they even pull this off? Well, they used this really cool device called a Josephson junction. The best way to picture it is like a tiny little sandwich. You have two layers of a superconductor with a super thin insulator in the middle. That insulator, that's the wall. And using superconductors was the secret sauce, because in those materials, electrons do this amazing thing where they pair up and act like one big, synchronized quantum object. And that is what allowed billions of them to do the impossible and tunnel through that wall together. And here's the kicker. They proved that these big, man-made circuits had what are called quantized energy levels. All that means is that the energy couldn't just be any random amount. It had to be on specific, discrete steps, kind of like the rungs of a ladder. That's a behavior everyone thought was only for single atoms. So what they had really done, in essence, was build a giant artificial atom. Think about that. They built a giant atom. And by doing that, they started to completely blur the line between the tiny quantum world and our own big, clunky reality. So that brings up another huge question, right? If this was so game-changing, why the huge delay for the Nobel Prize? Well, it just tells you how incredibly far ahead of its time this whole thing was. Seriously, just think about that for a second. 40 years. That's an entire career for some scientists. To put it in perspective, that's like the gap between the first person landing on the moon and the first iPhone coming out. A huge reason for the wait was that back in '85, this was an amazing discovery for sure, but nobody knew what to do with it. The technology to actually apply it, it just hadn't been invented yet. Okay, so why now? What finally changed? Why is a paper from the '80s suddenly the hottest ticket in town? Well, the answer has everything to do with a technology that is, right now, completely changing the world. It all breaks down like this. First, you have the discovery. They proved you could actually see and control quantum effects in an electronic circuit. That was huge, because if you can control it, you can manipulate it. And the ability to manipulate those weird quantum states on a little chip, well, my friends, that is the absolute fundamental building block for what we now call quantum computers. And that really puts it all into perspective. That's the bottom line. This discovery wasn't just some weird, quirky thing they found in a lab. It was the essential first step. If they hadn't proved you could build these artificial atoms, the whole idea of quantum computing might have just stayed an idea. And honestly, that's what makes physics so exciting, isn't it? It's when one experiment, one observation that seems completely impossible, like seeing a ghost pass through a wall, ends up cracking open a whole new universe of technology. It's that moment when you see the rules of reality itself bend, right there in front of you. So we kind of end up right back where we started with this huge, mind-bending question. Where does this leave us? I mean, if the boundary between the tiny quantum world and our big macro world is this blurry, what does that actually say about our understanding of the universe? It feels like after all this time, we're still just scratching the surface. And that line between our world and the quantum one is a whole lot weirder and way more exciting than we ever thought possible.